All right, here we are doing Calculus 12. Okay, so I thought I'd start with just a recap of a max-min problem just to get you back up and running. So, a max-min problem, so optimization problem and strategies. I think that's the most important part. It's not so much about the problem itself, it's about the strategy of how to do a max-min problem. So let's see here. I hope you can read this. If not, I'm going to make it a little closer. So optimization strategies. Number one, draw a picture and label the variables. Second thing is you want to focus on what you're maximizing and minimizing. So you want to get those formulas done. Number three, you want to get that formula or that relationship you have that you're focusing on in terms of one variable using other relationships that exist in the situation. And then comes the fun part of now going through the whole steps of sections 4.1 to 4.3 of now taking the derivative, finding the critical numbers of where the derivative is equal to 0, where the derivative does not exist, the endpoints or the domain or the realistic physical parts of the question that would be coming about, and then the first derivative test, and then followed by stating the answers. So I'll put that down there. I'm hoping you can be able to read that. If not, we'll play that by ear and I'll do something different to post that if it's not legible on the video. Alright, so here's the problem. The problem is we want to find the largest area rectangle that can be inscribed in a semicircle with radius 7. So again, one more time, find the largest area rectangle that can be inscribed in a semicircle with radius 7. So we're going to follow the process. Let's draw a picture of what that is meaning and label some variables. That's our first step. So I'm going to draw a picture of this to the best of my ability of a rectangle inscribed in a semicircle. So here's me. My boys are just going to bed. It's good times here. Here's me drawing a semicircle. Not bad. Looks more like an ellipse, but it'll do. And I'm going to draw a rectangle inscribed inside that semicircle, and so an inscribed would have to be corners would have to hit the corner or the edge of the circle. So there's my picture. Let me see if I can darken that. Sorry for the shadow, it's dark out. I can make shadow puppets though. What am I trying to do there? There's like, that's a bat. That's pretty good actually. Okay, so here we go. I'll move this down here. You know what? I'm gonna do this. This is the first time I've done this at nighttime. That should give me no shadow that side. Okay, that's better. Okay, so there's the semicircle with an inscribed rectangle, which I've drawn it the biggest that I can. So largest would mean I'm going to be dealing with a maximizing situation. I need to label some variables in here. Now I don't know this length here, and I also don't know this height or width, depending on what you want to call it. Now because I've got this on an XY axis, to make this easier, I'm going to call this X and this would be X as well because of symmetry. Hence this length here would be 2x, the way I've defined it that way. I could call that whole thing just one big X, but I like the reference to 0 to make it easier, so that's 2x. And then this here I'll call, for just obvious reasons, Y. Now I'm going to focus on the formula of what I'm trying to maximize. I'm trying to maximize the area. The area of a rectangle is length times width. There's my width. So the area is going to be y times 2x, or 2x times y. So that is there's my picture. There's the focus on my maximizing, minimizing. Now I need to get this in terms of one variable, and the trouble is I have two variables. So this is always the fun part. I need to find a relationship within that picture that can take the x or the y out of this. So as I look at this picture, one thing that I might see, and this might take some time, I have to play, I know that this has a radius of 7, and the radius is either here, which doesn't really help me because that's not really on the rectangle, but this is also the radius. That's 7. So looking at that picture, the way that I've drawn it from here to there, there's a relationship between x and y. There's a y, there's an x, that's a 7, this is 90 degrees. That just screams x squared plus y squared equals 7 squared. And I'm going to solve this for x or y. Probably solve it just because out of habit for y. Y is going to equal the square root of 49 minus x squared. Technically it's plus or minus, but I'm dealing with the positive length, or the positive length of y in this case. So then this will then replace here, and now I've got my area function for the area of the inscribed rectangle inside that semicircle. And now at that point, I almost draw a line because that's the hardest part. I am now thinking of the area function as like f of x, a of x is now this function. And instead of putting the square root, I'll raise it to the 1/2 power, just for derivative purposes. So now I'm on the road of, now I'm back to 4.1, 4.2, and 4.3. I'm critical numbers. I gotta take the derivative, find out where it's 0, undefined, endpoints, increasing, decreasing, first derivative test, state answers. So take the derivative. It's been a while. Don't forget the baby. So here we go. First function times the derivative of the second. That's going to involve a chain rule. 1/2 comes down, inside stays the same, lowers by 1 times the inside derivative of the baby, in this case is 2x, plus the second function, which is this guy, times the derivative of the first, and the derivative of 2x is just 2. So cleaning this mess up, these 2's cancel, and I'm left with negative 2x squared over the square root of 49 minus x squared when I take the negative and bring that to the bottom and then rewrite it as a square root, plus 2 times the square root of 49 minus x squared. So there's my derivative. I now have to do my critical numbers. So where is this equal to 0? I might get a common denominator first. That might be the wisest thing to do. So back here, if I put this over an imaginary 1, multiply this top and bottom by root 49 minus x squared, I would end up with negative 2x squared plus 2 times 49 minus x squared, because I'm multiplying that by the root 49 minus x squared. And doing a little bit of cleanup on this guy, what do I end up with? I would end up with minus 2x squared plus 98 minus 2x squared. So it ends up with 98 minus 4x squared over 49 minus x squared square rooted. So where does that equal 0? So there's my derivative. I cleaned it up there. I didn't initially, but I did some cleanup to make it easier to solve. Where is this equal to 0? That's where the numerator, 49 minus 4x squared equals 0. That would be where x equals the plus or minus square root of 98 over 4. or in this particular case, what would that end up reducing to? What's that look like? I know that'd be 49 over 2, so I could write that. Could be 7 over root 2, or 7 root 2 over 2. And plus or minus, but I'm just dealing with the positive answer at the moment. Okay, so there's my x value. Where is it undefined? Would be where the denominator is equal to 0, and that would be where 49x squared equals 0, and that would be when x equals plus or minus 7, or in this case 7. And then I should also talk about endpoints. The physical endpoints of this as far as the actual rectangle. X could be as small as 0, because then I'd have no length to it, and as big as 7. So between 0 and 7. So x equals 0 and x equals 7 are my endpoints. So there's my critical numbers. So critical numbers are x equals 0, x equals 7 root 2 over 2, and x equals 7. Then I would go to my first derivative test. So I'd be like, okay, here's my first derivative. On my number line, here's 0, which is like an endpoint. 7 is an endpoint. 7 root 2 over 2 is a 0, sorry. And then I would test those intervals. So the derivative here I might test, for example, that's bigger than 1, so I'd test 1. Go back to my derivative here. If I plug 1 into this, I get positive. That's a positive number. When I plug 1 in for x, that's positive, so this is a positive value, which I was anticipating because I know this is going to be a max, but I'm just proving it to myself. And plugging in here, yeah, that's going to be 6 would be a good number to plug in. So plugging in 6, 36 times 4 is well bigger than 98, so this is negative and that's positive, so this is negative. So it's going down. And so right there, I would know you have a max at x equals 7 root 2 over 2. You then also have a minimum at your zeros and 7. And so the question wanted the largest area. So now we can find the max area. Max area would equal, well, my corny answer would be a of 7 root 2 over 2.